Hello, welcome back. In this talk, we are going to talk about the equations of motion. These are the equations that govern all the motion in the ocean. In this talk, we're going to focus on acceleration and the acceleration terms that affect the motion in the ocean. Then in the next talk, we're going to see how the acceleration is affected by the pressure gradient force, gravity, Coriolis, friction, and other forces. Talking about forces, let's think about forces again for a second. So what do forces do? Well, if we think back to Lab 1, we saw that force is equal to mass times acceleration. F equals ma. That is Newton's second law. And we can put that into words, and we see that a net force causes an object to accelerate with an acceleration directly proportional to the size of the force. So looking over here at this diagram, we see that the acceleration here on the y-axis and the force on the x-axis. If we increase our force, we increase our acceleration proportionately. So if we increase the force, the acceleration increases proportionately. We have a linear relationship between force and acceleration. So if you push harder on something, it will accelerate more. This is Newton's second law, F equals ma. So now for a particle of mass m, if we divide through by m right here, we end up with the acceleration equals 1 over m times the sum of those forces, F net. All right, we're going to use this expression right here to develop the equations of motion that govern the ocean. All right, so we're starting with the idea that acceleration equals force over mass, Newton's second law. And that's great when we're talking about a baseball or a box, when we're looking at something simple, when we're doing our intro physics classes. However, we're talking about the ocean, and the ocean isn't a ball. It's not a box. It's a fluid. So we can't talk about its mass. Instead, we talk about its mass per unit volume. Similarly, we talk about the force per unit volume. So the mass per unit volume, we know, is the density, where the density is the mass over the volume. And if we rewrite this expression using, instead of mass, using the mass per volume, or the density, and instead of force, using the force per volume, we get that our acceleration equals 1 over the density times the force per volume. And just to check to make sure that this does in fact satisfy Newton's second law, we can bring this expression down here, and we're going to now replace the density right here. We're going to replace this density by the mass over the volume. And it's 1 over that. So instead of writing mass over volume, if I put 1 over that, I end up with the volume over the mass. Multiplying that by the force over the volume, and I realize I can cancel my volumes. And so what I'm left with right here is equal to 1 over the mass times the force, which is exactly what we had to begin with, Newton's second law. All right, so using our expression, let's get started. All right, so we have in words here, this acceleration right here is equal to 1 over the density times the sum of the forces. And those forces, we're familiar with those now, gravity and pressure gradient force and Coriolis and friction and any other forces that are acting in the direction that we are interested in. So let's focus first on the acceleration. All right, we remember back to Lab 1 again, that the acceleration is equal to the change in the velocity with time. So it's the change in the velocity with time. And we can write that as the acceleration is equal to the change in the velocity over the change in time. And we remember that if we allow delta t to go to 0, this becomes dv dt. We can also remember that the velocity itself is the change in the position over time. So if we think about this velocity here as the change in the position with time, we can get that the velocity equals the change in the position, which I'll go ahead and do as a y. So that'll be dy dt. All right, let's do a little review, reminding ourselves about this velocity and how we talk about the velocity vector in the ocean. So we remember that the velocity vector in the ocean is divided into 3 different dimensions. And the first direction that we have is our x direction, our east-west direction, our zonal direction. And for that, we talk about the u velocity. That's the u velocity is for the x component of our velocity. Now, in the north-south or the y direction, that's our meridional direction. And what's important in this case, what we call this component of our velocity is v. So we use v in the north-south direction. And in the vertical direction, the up-down direction, the z direction, we use w. So the 3 components of our velocity vector, u, v, and w. Now, if we look at this diagram right here, the other thing that we see is that the velocity itself, as I mentioned, is the change in the position with time. So we can also say that u equals dx dt, and we can say that v equals dy dt, and we can say that w equals dz dt. All right, let's start thinking about acceleration. So the acceleration in the x direction is going to be du dt. The acceleration in the y direction will be dv dt, and the acceleration in the z direction will be dw dt. I've used capital D's here because what we're going to need to do is take the total derivative. So let's look at that and understand what's going on by starting in the x direction. So in the x direction, we have du dt. Again, I said this is called the total derivative because u is not just a function of time. U could be a function of many things. It could be a function of x, it could be a function of y, it could be a function of z, and it could also be a function of time. So if we want to look at how at u as a function of, if we want to take the derivative of this, knowing that u is a function of x, y, z, and t, then if we take the total derivative of u with respect to time, what we need to do is take the partial derivative of u with respect to x first. And then we can't just do that because we need the derivative with respect to time. So we have to do the chain rule and do dx dt. Now, we also need to take the partial derivative of u with respect to y. And we also need to take the chain rule, so we do dy dt. Then we can take the partial derivative of u with respect to z. And again, the chain rule gives us dz dt. And then we still now can take du dt. And we can write the chain rule here if we want to, dt dt. But we know that's just one. So what we get is du dt equals du dx dx dt plus du dy dy dt plus du dz dz dt plus du dt. Now, what we notice is that, as we just pointed out, right here we have dx dt. Well, that we know is just u. So this part right here is just du dx times u. All right. Well, right here we have dy dt. Well, that we just saw is v. So this is du dy times v. And right here we have dz dt. And we know that that is just w. So this is du dz times w. And then right here we just have du dt. So this is now the total derivative that we get when we bring all of these pieces together. All right. So if we take the total derivative of u with respect to t, and we get what we just had a second ago, then we can rewrite this and bring du dt to the front and just rearrange our terms. So we have du dt plus u du dx plus v du dy plus w du dz. And this is what we call the total derivative. So expanding that out in all three dimensions, we see what we have for x. And then we can also look at how we can break this down. The very first term here, du dt, that is what we call our local acceleration. That's if we were just floating along with the water parcel, that's how it is changing in time. The other terms, these terms here are our field acceleration terms. This is the advection terms. But what we mean here is if we're looking at this as a field and we're looking out at the ocean at different points and we see that the velocity might change might be changing spatially. And so it is these are the advection terms or the field acceleration terms. Looking at these pictorially, we see right here we have our local acceleration, which is just the simple acceleration that we talk about normally, where we have our change in our velocity with time, and that gives us an acceleration. So in this example, if as we're going from point X to point X1 to point X2 to point X3, we see that we're going there faster from point X1 to point X2 than we are from point X2 to point X3. So V1 is faster than V2. And so our acceleration is in the opposite direction. This is our local acceleration. This is du dt. If we look at the advection terms, what we see in this case is that as we're changing the field, as we're moving to a different point in the field, that is when our velocity is changing. If we're changing in terms of where we are in x, we see that the velocity changes based on where we are in x. So those are the advection terms, or the field acceleration terms. All right, so that's all I have for you for acceleration. Next, we're going to get into looking at the rest of these terms. We have gravity, pressure gradient force, Coriolis, friction, and other forces.